Students, you are welcome to another episode of our lecture. Today we are going to look at electronic configuration and rules governing filling of electrons into orbital. In my last lecture, we were able to look at the solutions to Schrodinger wave equation. The solution gave us four quantum numbers. In fact, it is the combination of Schrodinger and Dirac that gave us the four quantum numbers. We have the principal quantum number n, we have the azimuthal quantum number L, we have the magnetic quantum number, and we have the spin quantum number. The principal quantum number tells us about the energy occupied by the electron. The azimuthal tells us the geometry of the orbital. The magnetic quantum number tells us the spatial orientation of the electrons in the orbital. And the spin tells us the spin of the electron, either in a vertical form or opposite. So what we are going to do tentatively today is to look at the different types of orbitals we have. From the solution to the the Schrodinger equation, we arrive at about four orbitals. We arrive at the s orbital, we arrive at the p orbital, we arrive at the d orbital, and we arrive at the f orbital. Now, from our solution, we're able to know that we have one s orbital. We're able to also know that we have three types of p orbital. We are able to know that we have five types of d orbital. Three types of p orbitals we have the px, the py, the pz. When you look at the magnetic quantum number and subsidiary quantum number. And we have five types of d orbital. The five types of d orbital are the dxy, the dyz, the dzx, the dx square minus y square, and the dz square. These are the five types of d orbitals we have. And we have seven types of f orbital. Now, these are the orbitals we have. Now, how do these electrons get accommodated into these various orbitals? That is writing the electronic configuration of elements. There are rules governing such filling of orbitals, filling of electrons into orbitals. We have the Aufbau rule, we have the Pauli exclusion principle, and we have the Horn's rule of maximum multiplicity. We have the Horn's rule of maximum multiplicity. Now let us look at the Aufbau rule. What is the Aufbau saying? Aufbau said in filling electrons into orbital, you have to start with orbitals of the lowest energy progressively until you get to the orbital of the highest energy. The electrons goes in singly before from that of the lowest energy before it's moving. It cannot just move in. You cannot start filling the electron into orbital from that of the highest energy level. So let us look at this demonstration. We run, these are the various orbitals. We have the 1s orbital, the 2s orbital, 3s, 4s, 5s, 6s, 7s, and up to 8s orbital. And we start from the second row, the 2p orbital, the 3p orbital, the 4p, the 5p, the 6p orbital. Then we move into the 3d, the 4d, that is the third row, the third column, the 4d and the 5d orbital, and we have our 4f and 5. These are the highest orbitals attainable. Now, if you run an arrow across, this, just run an arrow across. This is just to tell us on how we are going to comfortably fill the energy level. We are going to fill the orbitals in accordance to increase in energy level. Now, the 1s orbital has lesser energy than the 2s orbital. The 2s orbital before the 2p orbital, before the 3s orbital, before the 3p orbital, before the 4s orbital. So if you have to fill in, you just follow this format in filling in electron into various orbitals. Now, what is Aufbau saying? We said Aufbau said you fill in from the lowest energy before you proceed to the highest energy. And how do you fill in? You have to know the atomic number of the elements in which you want to fill in the electronic configuration, because the atomic number is the number of protons and it's also equal to the number of electron in a neutral atom. We can also fill in, write in electronic configuration for ions, but for now let us just take for just element X, assuming we just pick an element X with atomic number of 8. How do we fill it? How do we write the electronic configuration? So we can write the electronic configuration in this format. We write 1s, the first electron goes into the first shell with the lowest energy, 1s2, remaining, the atomic number of this X is 8. 2 from 8, we have 6, then followed by 2s. 2s can accommodate maximum of 2, which is 2, remaining 4. The 4 will now move to the next. The next is the 2p. The 2p can accommodate maximum of how many? The 2p can accommodate maximum of, we have 3 types of P orbitals, and these P orbitals are degenerate. We refer to them as degenerate orbitals. These are orbitals of same energy. So we have the px, the py, and the pz, the 2pz. You can fill in, because they have the same energy. You can fill in any of the P orbitals, but preferably you start from the px orbital before the py and the pz. So 2 plus 2 is 4. We have remaining 4. The remaining 4 it can goes in like this: 1, 2, 3, 4. 1, 2, 3, 4, which is 1s2, 2s2, and 2p4. This is that for an element X with atomic number 8. That is what the Aufbau is telling us. You have to start filling from the least energy, from the orbital with the least energy before that of the higher energy. Now let us look at Pauli's exclusion principle. What is Pauli saying? Pauli is saying that no 2 electrons can have the same 4 quantum number alike. No 2 electrons in an orbital can have the same 4 quantum numbers alike. That is, at least one of the quantum number must be different in the electron we are considering. At the same time, he said no orbital can accommodate at the same time more than 2 electrons. No orbital can accommodate more than 2 electrons. So if you are filling into the orbitals, you have to fill in the moment. Let us take a lithium, for example. Lithium, the atomic number of lithium is 3. 1s maximum is 2. Then the remaining one has to go to the 2s orbital. The remaining one has to go to the 2s orbital. You cannot say 1s3, because the maximum electron that can be contained in any orbital, according to Pauli exclusion principle, is 2. According to Pauli exclusion principle, is 2. Now let us look at Horn's rule. Horn's rule of maximum multiplicity. He said that in filling orbitals of degenerate orbital, in filling electron into orbitals of degenerate orbitals, the electrons has to go in singly before pairing. It has to go in singly before pairing. That shows, let us take our oxygen, for example. Oxygen has an atomic number of 8, and we have a nitrogen with atomic number of 7. Let us look at it. You can say we can also use a box to represent the orbitals. assuming this is the 1s orbital, this is the 2s orbital, and we have 2p orbital. That is px, this is px, py, and pz. Now let us see how we are going to fill it in. We have to start with, according from the Aufbau principle, assuming we have to fill in for nitrogen with 7 electrons, it has to be 1, 2, remaining 5. The second filling goes into the second orbital, which is the 2s orbital, which is 1, 2. And the electron has to be of opposite spin. There has to be of opposite spin. That is for remaining 3. The 3 electrons, this is 1, 2, 3, 4. 4 from 7, we have 3. 3 electrons, you can as well fill in 2 electrons here, 1 here. No. Hall's rule said you have to fill in of maximum multiplicity set. You have to fill in singly before pairing. So the electron has to fill in singly, single, 1, 2, 3, before what? Pairing. So if you are considering another element now, for example, oxygen, that has 8 electron at its ground state, you can fill it in this format: 1s with the 2 electrons of opposite spin. You now move to 2s with 2 electrons of opposite spin, and this is 1, 2, 3, 4, remaining 4. The 4 electron, we have how many type of degenerate p orbital? We have 3 types: the px and the py and the pz. So how do you fill it in? According to Hall's rule, you have to fill in singly, 1, 2, 3, and we have 1. The remaining 1 will go to the first, the px before pairing, and you have to do that. And the pairing has to be of opposite spin. This is just to reduce repulsion. This is just to reduce repulsion between the electrons. If they are of the same spin, what do you expect? There will be repulsion. So they have to be of opposite spin to reduce repulsion. So this is just what it takes to fill in our electron into orbitals. But however, we have to just look at filling in electrons into orbitals of ionic compounds. Filling in electrons into orbitals of ionic compounds. Let us see how we are going to fill in electron into sodium atom. The sodium has 11. The atomic number of sodium atom is 11. We write it in this format: 1s2, 2s2, 2p6, and 3s1. This is that of sodium. Now, what about sodium ion? Because let us look at filling in for sodium ion. Sodium ion, assuming sodium loses 1 electron. It loses 1 electron at the ground state. Before losing the electron, it was 11. The atomic number is 11. Now, if it loses an electron, it becomes a sodium ion. And by the time it becomes a sodium ion, 1 positive, it has lost 1 electron. So instead of writing the atomic configuration using 11 electron, you don't have 11 electron because it has already lost 1 electron. It is now 10 electrons. So you now rewrite it in this format. That is, you now write it with 10 electron: 1s2, 2s2, 2p6, 3s, nothing, because it is off. So there's no point to put the 3s there. So the electronic configuration of sodium atom, it is this, and that of sodium ion is this. That is that. And at the same time, we can also look at chlorine and chlorine ion. We can look at chlorine and chlorine ion. The atomic number of chlorine is 17. Atomic number of chlorine is 17. So we can easily write it as chlorine 17, 1s2, 2s2, 2p6, 3s2, 3p, this is 2 plus 2, 4, plus 6, 10, 10 plus 2, 12, then 5, 3p5. This is for chlorine atom. Now, what about for chlorine ion? Probably by the time the sodium loses its electron, chloride atom that is highly electronegative, it has a very strong affinity for electron, can easily grab that electron. We are going to look into that by the time we start doing our chemical combination. It can easily grab that electron. By the time it grabs that electron, what happens? It changes from the 2p5 to 2p6. It changes from 2p5 to 2p6. So we have to rewrite it, and if you are writing it for chlorine ion, that is chlorine atom plus electron, it becomes chlorine negative. So what do? You have to rewrite the electronic configuration of chlorine ion, which is 1s2, 2s2, 2p6, 3s2, 3p. Instead of 5, it becomes 6 because it has gained an additional electron to become chlorine ion. Now, one other thing I want us to understand again, we can also abbreviate it. Instead of writing all this 1s2, 2s2, we can abbreviate it. We can go to our group 8 or group 18 of the periodic table, where we have our inert gases or the noble gases. We have our noble gases from helium to neon to krypton to argon to radon to xenon. We have our noble gases. We can use their configuration. It eases us a lot. And let us start from lithium. Let us start from lithium. The atomic number of lithium is 3. The atomic number of lithium is 3. Lithium is 3. And if you have to write the electronic configuration, 1s2, 2s1. And instead of just going, you can easily, and whereas this 1s2, helium, the electronic configuration of helium is, because it has just 2 electrons at the outermost shell, so you just write 1s2. So instead of writing the 1s2, you can use it to represent helium. You can use this one as s2. It will now be electronic configuration of a lithium atom at its ground state. You can represent it as a helium core 2s1. It's as simple as that. And you can also go to that of sodium, for example. You can go to that of sodium, for example. If you go to that of sodium, 1s2, 2s2, 2p6 is the atomic configuration of neon, yeah, which has 10. Yeah, it's a noble gas. It has the atomic number of 10. Instead of writing all these lots, you can rewrite it, and you put you can rewrite it. And instead of writing, let us look at it. Sodium is 1s2, 2s2, 2p6, and 3s1. And we said neon is 1s2, 2s2, 2p6. It's a noble gas. It has a complete outermost complete orbital. It has a complete orbital. So what do? You can just write, instead of all these lots to this point, which is equivalent to the neon, you can just write neon core 3s1 for what? For sodium. So that is that. And I think with this, we tentatively we can write some of the electronic configuration of elements. All what we need is the atomic number, the number of electrons that is involved, and we are good as done with it. Please, my students, I will advise us, while we are still staying at home, we shouldn't hesitate not to read our books, because by the special grace of God, we are still going back to school. The essence of what we are doing now is just a reminder. You are supposed, after each of these lectures, you go back and go through and read, so that you're refreshing your brain on some of the things that we have done. By the special grace of God, we are going to look at chemical bonding in our subsequent lecture. We are going to look at chemical bonding in our subsequent lecture. We are going to look at various types of bonding, the ionic bond, the covalent bond, the dative ionic bond, and the rest. I wish us a good stay at home while we make sure that you still go back to your book and you read while hanging on at home. Thank you very much for listening.